Welcome back to Mechanics and Control of Robotic Manipulator. This particular lecture called lecture 11, and so far what we have seen is actually like we have talked about position. So in the sense we have seen actually like angular and as well as linear position. So these are actually like we have seen in the sense in very broad sense what we have seen actually like we have seen the geometrical model. Okay, so that is what in robotics what we call it is robot kinematics, the sense study of motion without considering the force and inertia. But what we have seen is actually like only the positional model, so that's what we call robot kinematics. Now in the sense what I have, that is position vector and as well as what I call the orientation vector, all I am generally calling as a P of t. So what I am trying to do is actually like even the t is not coming here, but what we can see that now I assume that the position is with respect to time. I am differentiating that with respect to time. So then what we are doing actually like we are trying to do the kinematic model, but we are trying to do a differential, in the sense we are differentiating this. So this particular lecture would be talking about the differential kinematics. So in the sense, so velocity I call velocity kinematics. So differential or velocity kinematics, which we are going to see. So let me actually like go further on the course or further on the lecture. So as usual, like we will be giving the disclaimer. So this particular lecture, although not containing many of you can say other resources, still I wanted to give this disclaimer. So let me actually like go what exactly we are going to cover. We are going to talk about differential kinematics, in that sense what is forward and what is inverse differential kinematics we would be discussing. So on that we will come with one specific transformation matrix we call kinematic transformation matrix, but that in differential level, so we call that is Jacobian, and the Jacobian would be a rectangular. Then how we can take inverse, so we would be using more Penrose pseudo-inverse, and then we'll see that the multiple body will be having you can say velocity information, how one body to another body would be transferred. So that is what we call velocity propagation, and then we will see one simple example how we can actually like achieve. So in the sense we are actually like going very slow phase. So we'll first talk about what is kinematic model. So we know like a forward kinematic model where we can see mu is the task space vector, or what you call operational space vector, and q is your configuration or joint space vector. So in general, if it is a three-dimensional space, so the mu is a vector of you can say 3 linear position and 3 orientational information. So in the sense x, y, z and alpha, beta, gamma is the you can say the operational space vector. But what the joint space or you can say configuration space, so that would be consist of you can say as per Danawit-Attenberg, that would be consist of several you can say single degree of freedom joints. So in the sense it would be actually like either translation joint or rotation joint. So then you can see the q is vector of either theta or d. So I assume that n is my number of active joints, then you can see number of axes. So then you can see that it vary from you can say 1 to n. So the variable would be either theta or d. So that is what I've actually like mentioned here. So now this is what we know, and this particular model what we call you can say kinematic model, and this is straightforward for given you can say configuration space variable, and you are trying to find out what is the operational space. So that is what it is called forward kinematic model. Whereas so if you are actually like trying to find out you can see like for given mu, so what is your q, that is what we have seen as a inverse kinematic model. But in this particular interest we are not seeing that. So what we are trying to see, instead of that we are actually like seeing that this equation if I differentiate, so what I will get information of you can say the configurational space velocity. Okay, so the other side is actually like you will get operational space velocity. So in the sense you can see that one side would be having a configuration space velocity, the other side would be operational space velocity, and there would be a mapping tool. So that is what we call Jacobian. So this we will get it. So in the sense what we are trying to do, we are trying to differentiate the equation 1 and what happens, that's what we are seeing. So in the sense you can see that so mu is function of time and q. So in the sense I am actually like seeing that that is actually like mu is actually like function of time, then differentiation is mu dot. So the mu dot is actually like nothing but d mu vector divided by dt, and q dot is actually like nothing but you can say dq vector divided by dt. So this is vector, so I am actually showing. So whenever I am using in my slide, so if it is a bold letter, so that means actually like a vector, and dot is something like you can say differentiation. If I have double dot, then that would be d squared mu divided by dt squared. That way you can actually like take it. And now you can see that the differentiation will be coming here, since the mu is function of q and q is actually like function of time. Then you can see that this would come as a partial derivative. That partial derivative is in the form of matrix, and this particular matrix is nothing but Jacobian. Why it is come as a Jacobian? Because that you can say differentiation with respect to scalar, so that is actually like another vector, but differentiation with respect to you can say differentiating a vector with respect to another vector cannot be directly done. So which is actually like consists of partial differentiation with respect to that vector, and then you will be taking the time derivative. So that philosophy as given with Jacobi. So that is what we are actually calling that particular information called Jacobian information or Jacobian matrix. So here you can see that this q dot is nothing but you call you can say the joint space velocity, and mu dot is actually like you call operational space or task space velocity, and this Jacobian is giving the information between these two, right? And that is what it is doing, in the sense it is actually like a mapping tool. So this mapping tool, what we are actually like calling a Jacobian matrix, and it is very straightforward. With the other case, it is kinematic transformation matrix, right? But it in a velocity level. Now you can see that there are two conditions there. So if I give q dot, what would be mu dot? That is actually like straightforward for a given q dot and given you can say the initial q. So then we can actually like find what is mu dot. So this is actually straightforward. There is other case where I have mu dot desired, and can I get some q dot? In the sense I am actually like inverting this J inverse, so or you can say J matrix, then multiplying with mu dot. That's what actually like it is indirect method, or you can say inverse. So in that sense, the you can say differential kinematics can be you can say further divide. One is forward differential kinematics, where the q dot is available and you are actually trying to find out what is mu dot for you can say given q and q dot. So in the sense you can see that here what we are trying to do, we are trying to take the manipulator and you are fixing the motor and you are rotating with a certain speed and see that what happened on the end point, right? In the sense you are actually trying to simulate if it is a numerical, and if it is a real time you are trying to analyze, or you can say understanding the system. But what we are doing in a velocity level. So this is what forward differential kinematics is, very straightforward with you can say kinematic model. The same way here the joint space variable is known and you are trying to find out the task space variable. The same thing you can extend, so where you are actually like given mu dot and you are trying to find out what is q dot. In the sense you have to see one inverse of matrix. So if this matrix is actually like exists, in the sense the Jacobian determinant is not 0, then this is exists, and that too like square matrix this is exists, then you can see this is what you call inverse differential kinematics. In the sense for a given or for desired your end effector you can say velocity, what I can give as a joint space velocity. For example, I want to actually like you can say release the ball with a certain speed, how I can actually like rotate and release. So in the sense it's something like you can say baseball, or you can say probably you can call cricket and all. You can see how we can do the bowling and all. So that way you can see this is inverse differential kinematics. It is actually like indirect. And one more thing, the Jacobian supposed to be you can say determinant supposed to be non-zero, and Jacobian matrix can be actually like rectangular matrix because n is the number of axes, and I assume that three-dimensional space, the 6 is the you can say this you can say three-dimensional space where three axis linear translation and three axis you can say orientation will come. In the sense the Jacobian matrix is 6 cross n, and if n is 6 then that is a rectangle, so you can say square matrix. But if n is actually like non 6, or you can say not equal to 6, then it would be a rectangular. Then you have to come back because the determinant cannot be done, in the sense J inverse is not directly exist, then you have to bring some kind of pseudo inverse. So the pseudo inverse one we are going to use is Moore-Penrose pseudo inverse. There are several ways we can even use singular value decomposition and all, but we are trying to use this Moore's pseudo inverse. So the J plus is pseudo inverse, J inverse is actually like your proper inverse. So in the sense for non-square matrix we will be using J plus. Okay. So now if I actually like given mu dot, I'm trying to find out Q dot. So what that means, so I have already seen what is my end effect and I am trying to see the configuration. Indirectly it's inverse, but what that means, you are trying to control the manipulator in velocity level. So in the sense you are actually like taking the motor already there, and this is the next link, and you want to see this link supposed to rotate or move in certain velocity, and you are trying to see what speed I can give it to the motor. That is what we are trying to see. In that sense you can see that now this is actually like forward and inverse differential kinematic model, and we will actually like move forward. So in the sense what we are trying to see, we are trying to find out what is pseudo inverse in general, and we are trying to see. So for that I am taking a J of Q is a general matrix where that is real, but it is actually like m cross n. So and if m equal to n, it is actually a square, and what you have seen already, you can see it is a square matrix. Further, so it is consists of linear independent columns or rows. Then what indirectly it says, the rank is actually like full size of m or n. So in the sense you can see that so the determinant is non-zero, right? So in the sense you can use you can say J of Q inverse is exists. So that is actually like adjoint of, you can say, J of Q. So divide by the determinant of J of Q, right? So this is what we have seen in our matrix algebra, and in the sense the determinant is actually like non-zero, then this is possible. Whereas if it is a square to rectangular, what will happen? So there are two conditions. So the m is actually like what you call your you can say the operational space, and n is your you call configuration space, where the m is actually like greater than n, in the sense I have number of joints are less than the number of, you can say, operational space. Very simple example, I take a planar case and I am taking a 2 degrees of freedom. Okay, so in the sense what I am actually like seeing that this particular space required, you can see x, y and psi, but I have only theta 1 and theta 2, right? So in that sense what you can see that it is actually like 3 cross 2, so where m is actually like greater than n, right? In this case what we can see, so we can actually like see that in the sense you can see how many number of columns. So there are actually like 2, and these 2 columns are actually like, you can see like you have independent column, then what you can see the rank would be maximum 2, in the sense what you can see. So this is actually like some kind of different matrix, which is nothing but this, right? So now if I actually like get this, what I can see, there is actually like possibility I try to make as a rectangular to a square matrix. I can do J transpose to J or J to J transpose, right? But if I take inverse of this, this is not directly inverse of this, but I am trying to do a pseudo inverse. What I am trying to do, so I am actually taking this inverse or this inverse, right? So right now for you can say simplicity, we will see what really the background, but what we can see here, this is actually like n is smaller. So what we can see that if I get a you can say J transpose and J, if I am combining, what is the smallest matrix which I get? So here what the smallest matrix I will get, if I take n cross m into m cross n, so what that means, this is J transpose to J. So what I will get, it is n cross n as the smallest matrix I will get, right? So that is what we are actually doing. What we are trying to do, we are actually like multiplying J transpose in the left. So that way what we call it is actually like a left inverse. Okay, so what that means, so you are taking a J transpose J and taking inverse and multiplying with the J transpose. So that is what equivalent to you call pseudo inverse. And here there is this square matrix, this determinant is non-zero, then the pseudo inverse exists, and this is left inverse. Why? Because the J plus and J would be I, but J into J plus is not I. Okay, so that is what the left inverse, and that is what I want to explain here. So now we will move forward, where you can see the other case, where in the planar case itself I have actually like 4 joints. Okay, so in the sense you can see that I have, so joint 1, joint 2, joint 3 and joint 4. Okay, So now in that case what I have actually like in the plane I have actually three positions two linear and one angular position supposed to be maintained, but I have independent variable are 4, theta 1, theta 2, theta 3 and theta 4. In the case what I will get, so I can see that the linearly independent rows are the possible in the sense, so it is 3 cross 4, the maximum rank is 3, that is what indirectly meaning the linear independent rows. So in the sense what you will see, the minimum you can say, or you can say smallest size of the square matrix would be 3 cross 3. So then what I can see, 3 cross 4 multiply with 4 cross 3, then you take inverse. So what that means, so this is J and J transpose you are taking. So in the sense you are taking J transpose into J transpose whole inverse. So this is what we are doing. We are actually like taking this inverse is right. So that's why it is called the right inverse. Okay. You can see that the inverse you are taking in the right hand side. So that is what you can say right inverse. In the sense your pseudo inverse is actually J transpose into, you can say J into J transpose of whole inverse. So in the sense this is possible and this pseudo inverse is available, and you can see the further the right inverse why we are saying, so J of Q into J trans, or you can say J plus of Q is I, but J plus of Q into J of Q is not I. Okay, that is what the meaning of left and right inverse. But I want to give little more detail. So for that what we are taking, actually like I am taking one of the textbook content, and we are trying to see there are two cases. One case where you have actually like m is actually like 3 and n is 2. In the sense you have m is greater than n. So in the sense how many equations are possible? So you have actually like, so you can see that in this case, so how many unknowns? 2 is unknown. And how many actually like equations? So 3 equations. In the sense you have 3 equations and 2 unknowns. In the sense you are trying to over constrain this equation. Okay, because you have only 2 unknowns, but you are trying to make 3 independent equations. So which means actually like it is actually like superimposed. So in the sense what we can do, this is a over specified situation, and what we can try to do, this is over specified is not really going to possible. In the sense you have a 2R serial manipulator, but it cannot maintain all 3, you can say required degrees. In the sense I cannot maintain x, y and psi with only theta 1 and theta 2. In the sense the solution is not possible if you are talking about simultaneous equation. But since it is actually like a robotic manipulator, we can see that which is giving the least, you can say norm. In the sense what we have equation, mu dot is J of Q into Q dot. So what is the norm? I can see that this, you can say we are interested to find out Q dot. So what I can see that if I say, so the mu dot into J, so mu dot minus J of Q into Q dot. So this I call as a vector, this length, in the sense second norm. So in the sense this length is actually like smaller, in the sense very close to 0, or if it is 0 then there is an exact solution, it's possible, but if it is actually like very close to 0, I am happy, right? In the sense what I am trying to take, I am trying to take an objective function where, so the L is the objective function, that L I am taking as, you can say second norm, in the sense 2 norm. So where mu dot minus J of Q into Q dot. So in the sense I am taking the distance, so the distance I am trying to take, you can say as small. So in the sense this 2 norm I can write as a transpose equation, as a, you call inner product. So mu dot minus J of Q into Q dot transpose, and mu dot minus J of Q into, so Q dot. So now this transpose I get it. So what we are interested is dou L by dou Q dot is 0, right? So if I obtain this, I am actually like done. So that is what I am trying to do. I am trying to minimize this. So dou L by dou Q dot is actually like 0, and dou squared L by dou Q dot squared is actually like greater than 0, then that would be minimum, right? If it is less than 0, then that is a maximum. But right now we are not interested to see that. So what we can see that this we are trying to find it. And since it is a partial derivative, and you can take this, and what you will get, so you will get this as the equation, right? So because it is having two things, so I am actually like taking this. So where I am actually like taking a partial derivative of this. So and you can see that this term will be there. It is look like a 2 square, actually like it is something like a capital X square. So what you will do, capital X into d of x, right? So that is what I am doing it. So I am actually like taking it, this actually like a transpose as a single term as a capital X, and then you can see I am taking a you can say partial derivative, this goes 0 and this would be remaining as minus j of q. So that's why this minus has come and this jf, and this is a transpose I am maintaining, okay, since it's a vector. So now what I got it, this is actually like supposed to be equal to 0. I'm actually like multiplying this is throughout this j of q. So what I will get, right? But this is actually like transpose. So this will come like this. Okay, whole transpose and j of q equal to 0, right? So what we can see again goes, don't go directly, go back, and what you can see that this is actually like giving this equation. I'm taking a small trick. So what I'm trying to take, I'm trying to take this one side and this is another side, but what you can see, so this is actually like j of q into q dot transpose, whole transpose into j of q. So now I am actually taking a transpose throughout. So what I will get, I'll get very simple. So what I will get, I take a transpose. So this whole transpose, in the sense both side I'm taking a transpose. So then j of q transpose into mu dot. So you know this in the matrix, and this you can say j of q whole transpose become this j of q transpose into this would not be having a transpose, right? So now you can see that if I take whole transpose, I will get this matrix. And what you can see, if this I take as here, so what I am trying to do, so this I cannot take inverse, but what I can see that I am interested to find q dot. This is already a square matrix. I can take that, so as a j of transpose of q into j of q into inverse and j of q transpose into mu dot. So the mu dot is known and we can find q dot. So this is what we have seen. You can see this is left side, so it is a left inverse, right? So this is what we have done. So now we'll move forward the same thing, but here what principle we have used? So we have used the least square method. So but the next case, this is what the left inverse. So you can see this is what we have done, and this j plus is this part, and the one condition is this square matrix determinant is non-zero, right? So we'll move forward where there are less equation than unknown, in the sense I already told, right? There are actually like 4 unknowns, but there are 3 equations are available. So then what you can see, it is underspecified. You have, you can say more number of solution. In theoretically say it is actually like multiple solution. Some people call infinite number of solutions. In the sense what we can try to see, there are possible solutions, but that solution, can I bring it to a, you can say least, you can say effect. In the sense, can I apply to minimum norm? So in the sense, I will get q dot as several solution. So in that solution, which is giving the minimum, okay? In the sense, I am trying to see the length of this q dot, okay, as minimum. This is what I am trying to give a condition, okay? Or this is what my objective function, provided there is one condition, what that condition says. So I will actually like apply that. So the mu dot minus j of q into q dot, okay, supposed to be 0. So in the sense here, what this is a constraint optimization. So that is what we are trying to do. So this is what my objective function, but that is substituted or subjected to this. So in the sense, you know, like constraint optimization you can use with the Lagrangian multiplier. So in the sense, L would be having, so minimum norm of, or you can say norm of this. Then you have Lagrangian multiplier, which I call lambda, okay, so which I call lambda, and I'll actually like take it. So lambda into, so mu dot minus j of q into q dot, and since it is actually like taking as a vector, so I'm taking a lambda transpose. So this is what my objective function, okay. So now what condition is there? There are 2 conditions. So dou L by dou q dot is minimum what we wanted, that is actually like 0. Further, so this dou L by dou lambda also supposed to be minimum, in the sense this equation supposed to be 0. So that is what we are trying to see. Then there would be 2 equations will come, and you can actually like see there are two unknowns and we are trying to use that equation. So first I am taking you can say the objective function partially differentiating with respect to q dot, and this is what the equation, and you can see this is equivalent to, you can say, 2 into q dot transpose into q double dot, in the sense here it is a partial derivative, it is just 2 q dot transpose. Okay, so that is what we are getting, and you can see that in this case also like you have one q dot and lambda transpose into j of q, and there is a minus sign. Okay, that is what we got it. So this is supposed to be equal to 0, and when we are taking only lambda partial derivative with respect to lambda, you can see this is the only equation and this whole equation will come. So that is what we are actually like taking it. Okay, so now in that case you can see that there are two equations are there and two unknowns are there. In that, one known is mu dot and another variable, you can say quantity which is known to us is j of q, and we try to relate that. So if I actually like equate this to 0, this is already available equation, right? So I don't want that, but what I'm trying to see, this equation I'm trying to see. So I'm trying to relate q dot with respect to lambda. So in the sense I am trying to equate, so in the sense this is the equation will come. So now this equation, what I can see, so I can see that the q dot I already got with respect to this equation, right? What equation I will get, so that I am trying to bring it. So this is the equation which I got it, and I am taking the transpose throughout, in the sense q dot equal to j transpose into, you can say, lambda, and 1 by 2 is a common, then you can take it out. So now what you can see, this I substitute to here, what I will get, so mu dot as something, right? So that is what we are trying to substitute. So this equation we know, and I am trying to substitute that lambda relation, in the sense I am trying to substitute q dot relation as in terms of lambda. What I will get, I will get lambda relation. So what I will get, lambda. So lambda is actually like mu dot is there, and this is actually like j of q into j transpose q, and you can say this is 2 mu. Then you can actually like see this is a square matrix, and you take inverse, then lambda is actually like j of q into j transpose of q whole inverse. Okay, and 2 mu dot, and 2 I take common out and substitute that lambda here. So this 2 goes. So what q dot as, so j transpose of q into j of q into j transpose of q whole inverse. So you can see that this is actually like right inverse, and you have mu dot as that case. So now that is what you can see, it is a right inverse, and this is what we call I can say under specified situation, and this is what we got it, and we substitute this and we get q dot relation, and you substitute lambda and you will get this equation, right? And further you simplify, this is what you obtain, and you can see this is nothing but j plus, and you can actually like go further, right? So now here what the condition, this determinant supposed to be non-zero. This is what you call pseudo-inverse. Now you know like what is pseudo-inverse and what is Moore-Penrose as given, and what is forward and inverse differential kinematics. Now I will actually like extend this lecture, may go to 40 minutes, but please excuse, I will actually like go little forward. So what I am trying to do, I am trying to see like velocity propagation, in the sense I am actually like taking one simple step. So this is one body and this is another body, we have another link further. So now you can see that this is grounded. Okay, so I take a random joint, so this is actually like joint I, and this is actually like joint I plus 1. Okay, so now what you can see, this joint is actually like rotating. So basically what happened, there would be angular velocity would be happening because of this, and there is a independent motor is happening here. Okay, since as per the Danavit-Attenberg, what you can see, this can be rotation, then that would be only theta I plus 1 plus, or you can say differentiation, right? So but what one can actually like see, so if I want to know the information of, you can see I plus 1 with respect to I, so what we can do, so I can take the information of I, right? And what I can do, this information is available with respect to this frame. So I am obviously what I can do, I can see the rotational information of I plus 1 with respect to I is known. So then I can see that this is actually like a theta, but this is actually like vertical, in the sense the third axis. So I can actually like see that is actually like only 0, 0 and theta I plus 1. But this is equivalent to what? So omega of I plus 1 with respect to I. But what I wanted actually like omega of propagation, in the sense I want to travel from this joint to this joint, because in the base this is 0, 0. So which I call omega 0 with respect to 0 is actually like 0, 0, 0, because that is a fixed body. Then I go forward what I can actually like see. That is what my interest. In the sense what is I am interested to see. So omega of I plus 1 with respect to I plus 1 frame. So for that what I can do, I can take this already known, but I can transform this to I plus 1 frame. So in the sense I know the rotational information of I with respect to I plus 1, I can do it. So what I already got, I got this. So I can actually like multiply this with respect to I plus 1 to I. So what I will see, this whole I will get, you can see the multiplication. So in the sense R I plus 1 to I. So what I can see, this would be remaining, and this to this, you know, this is just an inverse, and this would give identity. So that is what we obtained as the, you can say, angular velocity propagation model. And probably in the live discussion class we will see little more, but this is a velocity propagation model for the angular velocity case. So one frame to another frame, this is the propagation. So now what can happen if it is a prismatic joint? So this joint angle will not be there because that is constant, right? If it is a prismatic joint, so theta is constant, then theta dot would be 0, right? So this term won't be there. That's what you can see if it is actually like a simple prismatic joint. So only the previous joint angular velocity would be playing a role. So this is what we call propagation model. The same thing you can actually go ahead with what you call linear velocity. What happened to linear velocity? So there is a linear velocity vector. So VII is there, and angular velocity, which is omega I to I, is there. But when I see the I plus 1, what happened? This linear velocity of previous frame would be having a role. In addition to that, what happened? This is a radial distance, and this is angular velocity. You will get a tangential velocity, right? So this is actually like vertically rotate with respect to z-axis, and this is what you call your position vector. So the position vector and the angular velocity, in the sense omega cross r or omega cross p. So that is what you can see. This is the position vector, and this is the angular velocity vector, and whatever the normal direction, that is what you can see the tangential velocity direction. So in the sense when you go to the linear velocity, so what you can see, the V I plus 1 to I, that would be simply linear velocity of the previous. Then you have one step further, you have actually like previous velocity, angular velocity, that would be multiplied with, you can say, the position of I plus 1 with respect to I. In addition, if it is a prismatic joint, then that would be having, you can say, rotational information is known. Then what you can see, this is I to I plus 1, and you have 0, 0 d I plus 1. And this is what you can say velocity of, you can say, linear velocity of I plus 1 frame with respect to I. But what I wanted actually like I plus 1 velocity with respect to I plus 1 frame. So then you can see this is what you will multiply this whole with respect to r I plus 1 to I. So then you can see that this would be become this, and you multiply that with this, then this goes to identity, and this will actually like have it. And if it is a rotary joint, this would be d is constant, so then d dot will become 0. That is what we obtained for a rotary joint. And we will see if it is a prismatic joint, you can see that term is coming, right? So this is what the propagation model. I just wanted to give very lighter way, and I'll show some example, and then we can actually like wind up this particular lecture. So for the example, I'm taking a simple 2R serial manipulator, in the sense, so this is what I'm actually like trying to see. So what I can see, this is what the 2R serial manipulator, and this is theta 1, and this is actually like theta 2, and this is what you call theta 1 dot, and this is what you call theta 2 dot, and I'm taking a geometrical variable as L1, L2, and this is what I call 0, 0, and this is what my end effector point. Okay, so now this is actually like 0, 1, and this is 2, and this is 3. I am interested to see what would happen to the linear velocity of 3 with respect to 0, and what would be the angular velocity of 3 with respect to 0. This I am interested, in the sense what I am trying to see, 0, 0, 2, so 3 to 3, and V 0, 0, 2, you can say V 3, 3. I am trying to find out all the sequence. So for that, what we wanted actually, like you call the, you can say, rotational information, in the sense the rotation matrix of individual frame is required. So I can actually like find it, since it's in a planar case, and you can say third axis is actually like parallel to this. So x2 and x3 are parallel, and this is x1, and this is actually like x0. So you can see that x1 to x0 is actually theta 1, and x1 to x2 is theta 2, in the sense that is vertical axis rotation, which is nothing but z axis rotation. Then your rotation matrix is like this. Okay, and the position vector, you can see 0 to 1 is 0, 0, 0, and 1 to 2 is actually like you can see along x. So in the sense L1 0, 0, and you can see position vector of 3 with respect to 2, that is actually like L2 0, 0, right? So this is what we have obtained, and we are actually like trying to see what would be the stationary point. Stationary point is actually like ground 1. So this case omega 0, 0 is actually like nothing but 0, 0, 0. Okay, and velocity of linear velocity also like 0, 0, 0. Okay, so that's what we are actually like getting it here. You can see that base frame angular and linear velocity vectors are 0, and what you can see, in the sense we substitute here, it's a rotary joint. I'll try to propagate. So what this is actually like R1 to 0, in the sense rotation matrix of 0 with respect to 1, and here actually like this is omega 0, 0, and what happened, this is actually like 1 angular velocity is there, which is theta 1 dot, and since it's 0, then you can actually see omega 1 to 1, that is nothing but 0, 0 theta 1 dot. So then when you go to omega 2 with respect to 2, what you can see, that is you can say 2 to 1, okay, and you have omega 1 to 1, that is 0, 0 theta 1 dot, and you can see this is actually like 0, 0 theta 2 dot, right? And you know the rotation matrix here. So even you take transpose, you have to take, even you take transpose, you can see that the first 1 and 2 row doesn't have the third element, only third row is having third element. So then you can see that this would give 0, 0 theta 1 dot, and this would give 0, 0 theta 2 dot, right? In the sense you can see omega 2 to 2 is nothing but 0, 0 theta 1 dot plus theta 2 dot. That easily you can see from this picture. So this particular point, right? So what we are actually seeing, that would be having only theta 1 dot, but when you see here, this theta 1 dot would be accumulate. Even this joint is actually like 0, but this frame is actually like rotate with respect to z axis theta 1, right? Not independent, but it is actually like moving, right? That is, we need to take it. So that's why you can see this is what the you can say angular velocity propagation, omega 1 with respect to 1 we obtain, and omega 2 with respect to 2 obtain, and omega 3 to 3, it is actually like would be identity matrix, and there is this one, and there is no, you can say, active joint, so it is straightforward to get it, right? So now this is actually like angular velocity propagation. We'll see what is linear velocity propagation. So the linear velocity, this is going to be, you can say, a case. So we are trying to address v 0, 0, that already we have taken as 0, 0, and v1 to 1, you can see this is actually like c1 minus s1 0, because it's a transpose, okay, and this is actually like take it 0, 0, 0, and here actually like you see this is 0, 0, 0 multiply, cross multiply with what you call 0, 0, 0, right? So in the sense you can see that this whole actually like going to be 0, that easily you can justify, because so this particular, you can see, point is actually like with respect to base, and there is no linear velocity going to happen at that point, because 0 and 1 are actually like the same point. So you will not get any, you call the linear velocity on this particular frame 0 and 1, whereas 2 and 3 will be having, that is what we are interested to find. So in the sense v1 to 1 is 0, 0, and we are trying to see what happened to the second one. So in this case, this is actually like going to be 0, 0 theta 1 dot, and this is actually like L1 0, 0. And what is cross product? So cross product we will take it in a skew symmetricity matrix later on. Right now we'll take the conventional way I, j, k, and here actually like 0, 0, theta 1 dot, and this is L1, 0, 0. In the sense what term you will get it? Only j term, right? Right? You will get j term, and what you can see, this actually like again going to come. So the k term will not be there, but you can see I term will not be there and j term will be there. Okay, so that is what we can actually like see, and we can actually like try to find out. So in the sense what we can actually like see, we can actually like substitute that, and you can see then this would be coming 0, 0, 0, and this would be actually like L1, so 0, L1 theta 1 dot, and it is actually like minus of minus, it is plus, and this. So now the transformation matrix, which is actually like C2 minus S2 0, and this is actually like S2 C2 0 0 0 1. This is the transpose, and that is what inverse matrix, and then you can just multiply what happened. This is actually like S2 because 0 term is there, so S2 L1 and theta 1 dot. The second element would be C2 L1 theta 1 dot. That is what we obtain, and we will go a little forward. So in this sense, this is actually like this value, and this is actually like 0 0 theta 1 dot plus theta 2 dot. So in the sense you can see that this would be added as this term. Okay, and you actually like see this is a simple identity matrix, so that's why you got it. Already you obtained from this, and this would be added, so that you can actually like cross check on this point. So you can see that this is actually like rotating with respect to theta 1 dot. So what one can realize here, so the tangential velocity will be, I'm just drawing, so this is the tangential velocity. The tangential velocity would be L1 theta 1 dot. So that two component in x and y axis you can see. So what is this axis? This is what x1, right? And you are actually like seeing on the line of you call x, and this is what you can see, the theta 2 theta 1 and theta 2. So theta 2 is actually like realized, and L1 theta 1 dot is your angular velocity, which is actually like normal to the direction of this, and this is the direction of, you can say, theta 1 direction and normal to that. And what you have a theta 2, that component you are actually taking. So theta 2 component you are taking, and you are actually like seeing that. So I'll just show it. So this is theta 2, okay, and this is actually like normal. So in the sense this is actually like 90 minus theta 2. So in the sense what component will come here? So this is actually like sine theta 2 component, and this component what you have seen on the y axis, that is going to be your x component. Okay, that is what we are actually like trying to see. So that's why you can see these are combined, and when you are actually like seeing this point, so this point there is another tangential velocity which would be added. So that is what added, that would be in, this is x axis and this is y axis, and this is the line, so obviously that would be perpendicular to that. So that is what coming. So the same thing you can actually like go to the third axis, what you know. So L1 C1 plus L2 C1 2 is your x, and y is actually like L1 S1 plus L2 S1 2, and if I differentiate, x dot would be minus L1 S1 minus L2 S1 2, and it is actually like time derivative, then this is actually like theta 1 dot, and this is actually like theta 1 dot plus theta 2 dot, right? So similarly I am actually like writing here, so x dot, okay, so I am just writing it here. So x dot would be, so L1 you can say theta 1 dot minus S1 and minus plus L2 theta 1 dot plus theta 2 dot and minus S1 2, right? So y dot is actually like similar, so L1 theta 1 dot C1 plus L2 theta 1 dot plus theta 2 dot and C1 2, right? So in the sense I'm just rubbing it this, okay. So now you got this clarity, right? So now what you can see, the same thing what we are interested, so we are actually like seeing it further. So in the sense what you know already this, so you know this, and you know like the transformation matrix of 3 with respect to 0, and you know this, so you can actually like see what would be the velocity of 3, or you can say end effector point with respect to 0. So that is what we are doing it. You know this velocity we have already obtained from the previous, and then you are actually like taking the overall rotation matrix, and then you are actually like going to get. So you can see that this is the thing which you got it for you can say earlier time derivative, right? You can see this is what we got it. So minus L1 theta 1 S1, right? So minus L1 S1 theta 1 dot and minus L2 S1 2 theta 1 dot minus L2 S1 2 theta 2 dot. The same thing happened here. So now you can see that what here actually like x dot, y dot and z dot is 0. Okay, here what you can see, so this would be actually like theta 1 dot, theta 2 dot. I can make it. So since the third row is actually like 0, I can keep it. So what I will get, so I will get here minus L1 S1 minus L2 S12. This is minus L2 S12, and this is plus L1 C1 plus L2 C12. This is plus L2 C12. Okay. So now this is, you can see this is mu dot and this is q dot and this is j of q, because q is actually theta 1 and theta 2. This is a function. So this is what we obtain, and this is what you call Jacobian matrix, and that is what we have seen so far. So with that, actually like I have actually like covered the differential kinematics in a lighter way, and in the live discussion and short discussion we'll see little more with example, and even we see how the Jacobian matrix is useful further. All those things we will see further. Okay, so with that I am actually like closing this particular session, and we will see little more detail on this in further lecture series. Okay, thank you. Although it is 46 minutes, please excuse on this, and see you on next lecture. Thank you. Bye bye. Take care.